I want you to try something right now. Pause this video, go to your kitchen, and grab a large, shiny soup spoon. Got it? Good. Now look directly into the inside of the spoon, the part that actually holds the soup. You'll notice something immediately. Your reflection is completely upside down. Now flip the spoon over and look at the curved backside. Suddenly, you're right side up again, but your face looks stretched out and shrunken down. It's the exact same piece of solid metal. Why does it play two totally different tricks on your eyes just by turning it around? To answer that, we need to look at the one strict rule light always follows. As light travels through empty space, it moves in perfectly straight lines. When those straight lines of light hit a perfectly flat mirror, they bounce straight back at you. Your reflection looks exactly like you do, because the paths of light haven't changed. When you bend the mirror, you force those straight lines of light to change direction. This change in the light's path is what transforms the simple reflection your eyes are seeing. Look back at the inside of your spoon. This inward curve is called a concave surface. You can remember the name because it dips inward, like the opening of a cave. Imagine light rays traveling horizontally toward that bowl-shaped curve. Hitting the slanted wall forces them to angle inward, crossing paths at a single focal point. The image crosses too. Light from the top ends up on the bottom. That's why your reflection is upside down. Now think about the back of the spoon. That outward bulging shape is called a convex surface. Instead of pushing light rays together, this outward bump causes them to ricochet away from each other. By spreading the light outward, the spoon captures a much wider view of the room and compresses it into a tiny space. Crossing the rays flips the picture. Spreading them out shrinks it. You are manipulating what you see just by altering the shape of the mirror. While metal reflects light, clear materials like water allow light to pass directly through them. If you drop a perfectly straight pencil into a glass of water, it creates a very famous visual illusion. The pencil looks cleanly snapped in half exactly at the waterline. This happens because light zips easily through the air, but it hits a literal speed bump the second it enters something thicker and denser, like water or glass. When light hits a dense block, slowing down drags it into a new angle. This is refraction. Shape that glass into an oval, and we can use that bending to our advantage. The curves catch the light rays and aim them to a single point. Gathering scattered light and bending it into a concentrated focal point creates a magnifying glass. Combining the density of glass with carefully chosen curves gives us the power to physically steer light, bringing the smallest details right into focus. The tricks you see at your kitchen table with a spoon and a glass of water are the exact same mechanics powering advanced scientific instruments. Dentists use tiny concave mirrors, the exact same shape as the inside of your spoon, to bounce light and magnify the hidden areas behind your teeth. Engineers take that exact same concave shape and scale it up to the size of buildings. They build towering arrays of curved mirrors to bounce and concentrate sunlight until it generates extreme industrial heat. Even everyday vision correction relies entirely on refraction. Eyeglasses use precisely curved glass lenses to bend incoming light so it lands perfectly inside the human eye. And centuries ago, astronomers realized they could align these refracting lenses inside long tubes, catching the faint light of distant stars and bending it to bring the universe closer to Earth. The next time you pick up a glass of water or catch your reflection in a piece of silverware, take a second to look closely. You are watching the invisible paths of light bending and bouncing in real time. Whether we are examining a single tooth or mapping the cosmos, our ability to deeply understand our world depends on building simple curves that command the path of light.